After having understood the propagation characteristics of optical fiber, now we would look into how we can make components using optical fibers. The question is, why do we want to make components using optical fiber, and what kind of components do we require? We are going to use this optical fiber in telecommunication system, or we can also use it in a sensing system. So, when we use the fiber in a system, we require several components, and if we have the components which are all optical, then the data rate is not compromised. Also the complexity of the system decreases. So, we would like to have as many components as possible in optical domain itself, and preferably in optical fiber, because when we make components out of optical fiber, then it is easy to splice them with the transmission fiber or sensing fiber. The insertion loss is low, compatibility is better. So, in the next few lectures we are going to study some components and devices made in optical fiber itself or using optical fiber. What kind of components or devices we want to make or we want to study here are switches, then we have power splitter, wavelength filter, we may require multiplexer, demultiplexers, polarization controllers, fiber gratings, fiber amplifiers, and dispersion compensating fiber. So, we are going to study these components and devices in the next few lectures. The very basic component and very important component using optical fiber is directional coupler. What is a directional coupler? It is essentially a 4-port device. So, we have a fiber here, a fiber coming out here, a fiber coming out here, and fiber going inside here. What we can have using this? Well, if we launch power P in port 1, depending upon the parameters of this device or this component, the entire power may come out of port 3. Then it is basically a switch. You are switching power from port 1 to port 3. It may also happen that if you launch power in port 1, then 50% power comes out of port 2 and 50% out of port 3, then it is a power splitter. Or you can have a desired ratio of power here. You can also have, if you launch two wavelengths lambda 1 and lambda 2 in port 1, then it may happen that lambda 1 comes out of port 2 and lambda 2 comes out of port 3. Then such a component is demultiplexer. You can also input lambda 1 from here and lambda 2 from here, and both the wavelengths may come out of port 1, then it is wavelength multiplexer or WDM coupler. And all these components can be made out of directional coupler. So, what is a directional coupler? If we have two cores which are put together very close to each other and we launch light in core 1, then as this light propagates through optical fiber, this composite system, then there is a redistribution of power between the two cores, and after a certain length all the power will come out of the other core. So, there is a switching of power from core 1 to core 2. So, if I look at it as a 4-port device, then this is port 1, port 2, port 3, port 4, and if I launch light in core 1, then light may come out of core 2 in the output end. How does it work? if I have two well separated cores, of course there is a cladding. So, if I have two fibers which are very well separated and these are single mode fibers, then this fiber supports this mode, this fiber supports this mode, okay. And propagation of light in this fiber is not affected by the propagation of light in this fiber, because they are very well separated. But if I bring them closer, then what may happen, that now this is core 1 and this is core 2, then this fiber has mode which is like this, this fiber also has a mode which is like this. So, these two modal fields may combine like this if the separation between the two cores is not very large. So, there is possibility of combining these two fields in two ways. One way is they combine like this, another way is that the field in one core is like this and in another core it is like this. So, these two fields may combine like this or like this. We can see that this is symmetric field, this is symmetric about this point, the middle point, and this is anti-symmetric. Then what happens is that when you bring two cores together, then this is not the mode of the composite system. The light in this core is affected by this core and the light in this core is affected by this core. So, these are no more the modes of the system, that is, if I launch this pattern, it will not propagate as it is, it will not retain its shape. Similarly, if I propagate this distribution in this core, it will also not retain its shape. So, these are no longer the modes of the system, but now the modes of the system are this and this. So, if I launch this distribution, then it will retain its shape, it will propagate along the composite structure without any change in its shape, and it will propagate of course with certain phase velocity. Similarly, this distribution will also propagate without any change in its shape. So, now the modes of the composite system are this and this, and these are known as normal modes of the system or super modes of the system. So, now if I launch this pattern into this core, then this can be understood as the superposition of these two modes. When I launch this, it means I am exciting this mode and this mode equally, because you can see if I add them up, then this plus this will give you the power in this core, while they will cancel out. So, there will not be any power in this core. So, exciting core 1 with an appropriate field pattern is equivalent to exciting symmetric and anti-symmetric modes equally. Now, since these are the modes of the system, they will retain its shape. So, I can understand the propagation of this in the composite system in terms of propagation of symmetric and anti-symmetric modes, because they retain their shape, but they have different velocities. So, as they propagate, there is a phase shift accumulated between them, and if at any intermediate distance I want to know what is the field distribution, then I will have to superpose these two modes with their accumulated phase shift, and that will give me the resultant field pattern. Now, if after a certain length the phase shift accumulated between them is pi, then effectively this mode flips with respect to this mode. So, if now I am interested in finding out the resultant, then the superposition of these two will give you cancellation of fields here and addition of field here. So, the resultant field would be only in this core and no field would be in this core. So, this is how there is switching of power from one core to another core. So, if you launch light into this, then after a certain distance, which is known as LC, the coupling length, the minimum length at which the entire field couples from core 1 to core 2 is known as coupling length, then at this length entire power will get transferred into the second core. I am assuming that these two cores are identical. If I let it propagate further, then it will switch back to core 1 and then again to core 2. So, there would be periodic switching of power between the two cores. I can understand this with the help of a very simple example of a coupled pendulum. I can take an analogy of coupled pendulum. So, this is the refractive index profile of the composite system, where I have two cores and this is the symmetric state, and I can also have anti-symmetric state. So, I have symmetric mode and anti-symmetric mode of the system, symmetric normal mode and anti-symmetric normal mode. This is equivalent to the modes of a coupled pendulum. If I have a pendulum like this, which I have coupled with the help of this small string, then now if in this kind of pendulum I push these two bobs in one direction simultaneously and then release them, then the oscillations would be like this, and this will keep on oscillating in this state for infinite time if there is no air resistance. So, this is the mode of the system, and since both of them are going in the same direction simultaneously, they are moving simultaneously in one direction and moving together, then it is symmetric state equivalent to symmetric mode of the directional coupler. I can also have another possibility that I push one bob like this and pull another like this and then release them, then they will do like this, and they will keep on doing like this forever if there is no air resistance. Then this is nothing but anti-symmetric state, or which is equivalent to anti-symmetric super mode of, or anti-symmetric normal mode of the system. Now, what happens if I displace only one of them? If I displace only one of them and then I release, then what happens? We will see. Then this is equivalent to putting power into one core of the directional coupler. So, if you look at the actual picture, then this is the symmetric mode. This color is changing, it indicates that the power is going along the length of the fiber, along the length of the directional coupler. So, this is the field distribution at different lengths of the fiber. As the color changes, it means the length is changing. So, I am changing the length, but it retains its shape. So, the symmetric mode, it retains its shape, and this is equivalent to the coupled pendulum when these two bobs are moving together and they keep on doing like this, So, this is symmetric state of the coupled pendulum, this is symmetric normal mode of the directional coupler. I can have anti-symmetric when I displace one on this direction and another in this direction. So, they will keep on doing like this, and this is how this field is also retaining its shape when it propagates along the length of the fiber. So, this is anti-symmetric mode of the system, this is anti-symmetric state of coupled pendulum. If I now displace only one, then what I see that after certain time the rear one is stopped and the other one is in full swing, then the front one is stopped and the rear one is in full swing. So, there is periodic exchange of energy between the two bobs. Similarly, here if I have all the powers here at z is equal to 0, then as the power propagates along the length of the system, then the power periodically transfers from one core to another core. Okay, so, there is periodic coupling, power couples back and forth between the two cores. So, this is how by just a simple analogy of a coupled pendulum we can understand the phenomenon of coupling of power from one core to another core. So, how the power evolves? Okay, I can write down the power as a function of z, z is the length of the propagation. For a generalized case, where I have two cores brought together separated by a low index medium which is cladding, and I take a generalized case where these two cores are not identical. So, the core 1 supports a mode which has propagation constant beta 1 and core 2 supports a mode which has a propagation constant beta 2. Then at z is equal to 0, if I have entire power in core 1, that is P1, 0 is the power in core 1, then as the light propagates along the structure, the power in core 1 varies according to this and power in core 2 varies according to this. So, what we have P1z is equal to P1 0 1 minus kappa square over gamma square sine square gamma z, P2z is P1 0 kappa square over gamma square sine square gamma z. This can be obtained by using what is known as coupled mode theory. We are not going into the details of that here in this course. What is kappa and gamma? Well, kappa square over gamma square is given by 1 over 1 plus delta beta square over 4 kappa square. So, gamma square is kappa square plus delta beta square over 4, where delta beta is beta 1 minus beta 2, which is also known as phase mismatch, because beta 1 represents the propagation constant of the mode of core 1 and beta 2 represents the propagation constant of the mode of core 2. So, of course, if beta 1 and beta 2 are different, so there is a phase mismatch between them. And kappa is called coupling coefficient and it represents strength of interaction between the two cores. It depends on the fiber parameters, the core separation and the wavelength. So, if I have two identical fibers, then beta 1 is equal to beta 2, delta beta is equal to 0, and if delta beta is equal to 0, then gamma is equal to kappa. Okay. If you go back to this expression, let me retain this expression on the board, that P10 P1z is equal to P10 times 1 minus kappa square over gamma square, kappa square over gamma square, sine square gamma z and P2z is equal to P10 and this is kappa square over gamma square sin square gamma z. So, now if delta beta is equal to 0, then again if I go back here, if delta beta is equal to 0, then gamma is equal to kappa. Okay. If gamma is equal to kappa, then I will simply have P1z as P10 cosine square kappa z and P2z is equal to P10 sin square kappa z. If I plot them with respect to z, then I can see that P1z is cosine square kappa z where he is like this and P2z is sin square kappa z where he is like this. So, these are the plots of P1z over P10, this is P2z over P10. So, it is P1z normalized with respect to the input power and P2 normalized with respect to input power. What do I see here? That at kappa z is equal to m pi, if I have kappa z is equal to m pi where m has integer values, then P1 is equal to P10 and P2 is equal to 0, which means that at these points where kappa z is equal to m pi, I have entire power in core 1 and 0 power in core 2. On the other hand, at kappa z is equal to m plus half pi, P1 is equal to 0 and P2 is equal to P10, that is at these points where kappa z is equal to m plus half pi, entire power is in core 2 and the power in core 1 is 0. So, at this length entire power switches from core 1 to core 2. The power in core 1 drops down to 0, the power in core 2 increases to 1, normalized power. So, the minimum distance, this is the minimum distance at which the complete coupling takes place, then it is known as coupling length, okay, which corresponds to m is equal to 0 here. So, kappa z is equal to pi by 2 and z is equal to pi over 2 kappa. So, the coupling length is pi over 2 kappa. So, it depends upon what is the coupling coefficient. If the coupling coefficient is large, then the switching of power from one core to another core would happen at a very short distance. Let us have a feel of some numbers. If I have a typical single mode fiber and I am working at a wavelength 1300 nanometer, then typical value of kappa is about 0.2 millimeter inverse. So, LC would be about 7.85 millimeter, close to 1 centimeter. Okay. So, in this length the entire power will get coupled from core 1 to core 2. I can also make a power splitter out of it if you work at the point where you have the power in both the cores equal, then it is 50-50 coupler. So, you can work at this length. If the interaction length is this, which is LC by 2, then 50% power will be in core 1 and 50% power would be in core 2, then it is power splitter. You can have any ratio depending upon the length you choose, you can have a ratio. For example, if you choose this length, then you can maybe have 25% power in core 1, sorry 75% power in core 1 and 25% power in core 2. So, you can choose any ratio for splitting of power depending upon the coupling length. So, when Z is equal to LC by 2 or equal to pi over 4 kappa, I see P1 is equal to P10 by 2 and P2 is equal to P10 by 2, then there is a splitting, equal splitting of power between the two cores, then it is known as 50-50 coupler or 3 dB power splitter, and this will happen at certain wavelength because kappa is wavelength dependent. So, if it is 50-50 power splitter at lambda naught is equal to 1300 nanometer, then if I operate the same coupler at 1550 nanometer, the ratio of splitting would be of course different because kappa is different. So, that was the phase meshed case where delta beta is equal to 0. In general, if I have two non-identical waveguides, then delta beta is not equal to 0, and then the fraction of power that appears in core 1 can be given by P1z over P10, which is 1 minus kappa square over gamma square sine square gamma z, and the fraction of power that appears in core 2 is zeta, which is kappa square over gamma square sine square gamma z. Now, just look at it. If you look at this expression, then I have this kappa square over gamma square sitting here, which means that I cannot have the maximum value of zeta as 1. Of course, the maximum value of sine square gamma z is 1, but because of this factor I cannot have maximum value of zeta as 1. It depends upon what is the value of kappa square over gamma square. So, zeta max is kappa square over gamma square, which is equal to 1 over 1 plus delta beta square over 4 kappa square. Since delta beta over 2 kappa whole square is always positive, okay, and here it is 1 plus this thing. So, this kappa square over gamma square will always be less than 1. So, I cannot have 100% coupling from one core to another core. Let us see how much we can have. So, if I have delta beta over 2 kappa is equal to 0.2, I put it here, then zeta max comes out to be 0.96, that is 96% power can be coupled from core 1 to core 2. So, this is the variation of eta and this is the variation of zeta. So, you can see that only 96% power can be coupled from core 1 to core 2, but this is very small, delta beta is very small here. If I have delta beta over 2 kappa is equal to 1, then this zeta max is just 0.5. It means that the maximum power that can be coupled from core 1 to core 2 is 50%. So, the power in core 1 will oscillate like this and power in core 2 will oscillate like this, it will never cross 50% mark here. If I further increase delta beta and it becomes 4 kappa, delta beta is equal to 4 kappa, then zeta max is only 20%. Okay. So, if there is a larger phase mismatch between the two cores, between beta 1 and beta 2, then the coupling of power is not complete. Another thing that I see here is that the gamma, what is the value of gamma? Since kappa square over gamma square is this, and if I have delta beta over 2 kappa is equal to 1 and this is how the power varies, then gamma is equal to square root 2 kappa, and this gamma basically tells you what is the spatial frequency of oscillation. Okay. If I increase delta beta over 2 kappa from 1 to 2, then gamma becomes square root of 5 kappa, then of course the frequency of oscillations increases here. So, the oscillations in power become more rapid as the phase mismatch increases. So, this is another thing that I see here. This is how a 3D plot shows the two cases when delta beta is equal to 0. I launch power in core 1 and then there is a complete transfer of power in core 2 at certain length. You can see a dip which goes to 0 here, and you can see a peak which comes to 1 here. Okay. If I look at from the top and draw the contour plot, then you launch power in core 1 and at z is equal to LC there is complete transfer of power in core 2, and here the power in core 1 becomes 0. Well, when delta beta is not equal to 0, then you can see that it is not maximized and there is still some power left here. Okay. So, there is no complete transfer of power. This is much more clear from this contour plot. So, you launch power here, there is a transfer of power here at this distance, the maximum transfer, but this is not 1, there is no complete transfer of power. So, in the next lecture, after having understood the mechanism of light coupling between the two cores in a directional coupler, in the next lecture we would look into some more components which we can make out of this basic building block directional coupler. Thank you.